Alright, so welcome to the first video. The topic we are dealing with here is solutions. So when you think about solutions, you are thinking about sugar in water or salt in water. And when you think about a solution, you are thinking about a mixture that we call a homogeneous mixture. In that case, you expect all the components in your mixture or in your solution to be in one phase. For example, when we dissolve salt in water, especially when it is not saturated, it's very difficult to make out salt particles in water because all the salt particles have dissolved. In the end, we just have a single aqueous phase, or in this case, it looks like a liquid. So when you think about solutions, we are looking at two things. A solution must have a solvent and a solute. So what is the solvent? Most of the times the solution has a majority component and a minority component. So this majority component is known as a solvent. So what do we mean? In case of salt solution, normally the majority component will be water. So the majority component will be water. So we can say salt is dissolved in water to make a solution. In that solution, the water is the solvent. Then we have a solute. So a solute is minority component of the solution. So if we talk about salt solution, the minority component is salt. So we'll say that the salt is a solute and water is the solvent, because water is a majority component while salt is the minority component of a solution. But before we continue, let's talk about what we call thirsty solutions. I mean, when you are thirsty, you are looking for water, or you want to add water to your system. So what are these thirsty solutions? Some solutions will draw water to themselves. So this is important. When you think about thirsty solution, you are thinking about solutions that will pull water towards themselves, or that will draw water to themselves. Normally, solutions that are concentrated, when they get in contact with water, they will want to suck as much water as possible, or they will want to add as much water as possible to their system. For example, seawater. seawater contains a lot of things. So in seawater, we expect to have different types of salts. So the seawater has different types of salt, and because of that, it is a concentrated solution. And when seawater gets in contact with other systems, and these other systems also have water, what will happen is that the seawater is going to pull water from these other systems, especially when these systems are less concentrated. That's the reason people do not drink ocean water. So you can be on a trip on the ocean, you are thirsty, you want to drink some water, but you cannot drink the water because ocean water is thirsty water. And really, the thirsty water will be able to pull, or thirsty solutions is able to pull water towards itself because it has what we call a greater tendency towards mixing. So this one is important because we will deal with this topic at a later stage in this class. So a greater tendency towards mixing is important in this case. So the salt has a lot of things that need to be mixed, and then one of those things will be pulling water towards itself to make sure that this mixing is done effectively. That's why it is a thirsty solution. Maybe if I can go back to this thirsty solution just to elaborate more on what it does. So let's suppose a person has drank ocean water. So let's say we have the intestines here. In the body. Yeah, what is this thing doing? And then we have the water. In these intestines, and the surroundings of the intestines have also water. But now this water has salt because it is ocean water. So this is the inside of the intestines, and this is outside. So what's going to happen is, because this part is concentrated, so this is concentrated. This part is concentrated, it's going to pull this water from here to the inner part of the intestines. In that case, it is depriving. It is depriving this other part of water, and that is going to affect the cells in the body. That's what a thirsty solution is all about. Now, let's look at these solutions. What are the types of solutions? Normally when we talk about solutions, we are just thinking about maybe salt in water or sugar in water. But we have different types of solutions. One example is air. Air is a solution that is composed of several gases. There's nitrogen there. There is oxygen there. There is some carbon dioxide, some argon, among others. But when you look at air, you cannot make out the components of air. So we have gases mixing. That type of solution is known as gas to gas. Then we have liquid solutions. So we have three types of them. We have gas to liquid solution. So most of the carbonated drinks are example of this solution. Then we have liquid to liquid. In this case, an example is like ethanol, that is alcohol, and water. Then we have solid liquid. So an example is salt solution. Then we have solid solutions. One example of that is, or some examples, brass, bronze, and others. So like brass is a mixture of different metals. The same thing with bronze. It's a mixture of metals. And because you cannot make out individual metals within those mixtures, we call them solid solutions. Now, especially when we think about water and when we think about solutions, one important thing is, can something dissolve in a specific solvent? So when you make a solution, you are thinking about, I have a solvent, I have a solute. Can this solute dissolve in this solvent? Or how much of this solute is going to dissolve in the solvent before it can no longer dissolve? That what we call a saturation point. So to understand that, we talk about solubility. So this is the amount of substance or amount of the substance that will dissolve in a given solvent. So normally solubility, in this case we are giving it as grams. So grams per 100 grams. So we can say we can dissolve 36 grams of sodium chloride in 100 grams of water. That's what it means. Then we have important definitions. Soluble substances. So the things that can dissolve in a solvent are known as soluble substances. Substances that cannot dissolve in a solvent or that do not dissolve in a solvent are known as insoluble substances. So these are important terms about solutions. Now the question can be, why do the solutions form? Why do substances mix in such a way that they will form a single phase? The answer is, there is what we call nature's tendency toward mixing. This term we call entropy is a very important term. We are going to look at it again when we deal with energetics. But what is entropy? Entropy measures randomization of a system, or we can say dispersal of a system. The more random a system is, the greater the entropy. The more dispersed a system is, the greater the entropy. So in nature, things want to be in a dispersed state, or things want to be in a random state. So normally we expect the entropy of the universe, or the entropy, let's just say the entropy of the universe, to increase for a certain process to happen, or we want things to be more dispersed for a process to happen. And we'll understand this better when we deal with this topic. So let's look at mixing. When you mix substances, what are you doing? When you mix substances, you make them more random. That's what you are doing. When you mix substances, you make them more random. As you increase the randomness, the likelihood of mixing also increases, or the likelihood of forming a solution increases. So I can say the more the randomness, the higher the likelihood of forming a solution. So that's important. So solutions happen because most of the time we are increasing the randomness of the system, or we are increasing the entropy of the system. Also, to form a solution, you need to deal with some intermolecular forces. So as a reminder, intermolecular forces will happen between molecules. So intermolecular forces are very important for solution formation. We have three types of interactions that occur in the process of forming a solution. So the first one, a solvent is going to interact with a solute. So let's suppose we have a solvent particle and a solute particle. There will be an interaction between the two. So that's one interaction that is involved in the formation of a solution. The second interaction will be solvent-solvent interaction. So we say we have this solvent here interacting with another solvent, and then we have solute interaction. So the solute will interact amongst themselves. So really it's a complicated process because there are so many interactions going on, and these ones are three important interactions that you have for a solution to form. Two important terms that we need to take note of: miscible versus immiscible. What are miscible substances? So, for example, water and ethanol. If you mix the two, they are going to form a single layer. So in that case, you say these substances are soluble in each other in all proportions. Therefore, they are miscible. But there are other substances like water and gasoline or water and diesel. They are not going to mix. So that would be an example. If you mix water and diesel, you see that you have two layers. So this is layer 1. This is layer 2. So in that case, you say these ones are not mixing. Therefore, they are not miscible. Substances that are not soluble and form different layers are what we call immiscible substances. So those are two important terms that we can think about as we deal with solutions. Now, we have talked about intermolecular forces that are responsible for the formation of solutions. As a reminder, we discussed dispersion forces, dipole forces, hydrogen bonding, and then we have another force that is important in solution formation, that is ion and dipole. So an example is if you have a water molecule and then you have a sodium ion, there will be an interaction between the two. This water is a dipole. This sodium is an ion. When they interact, we call it ion-dipole interaction. So these are the forces that contribute or oppose the formation of a solution. For example, let's take dispersion forces like here. These forces. We have pentane and heptane. These two, These two compounds have similar type of forces. When you mix the two, they are going to form a solution because both of them are using the dipole forces, what we call London forces. That is, likes dissolve likes. Another example is acetone. Acetone and chloroform. Both of them are dipole. If you put them together, they make a solution for the same reason. Likes dissolve likes. Ethanol and water. Both of them have hydrogen bond. You put them together, they'll form a solution. Ion dipole. We have a dipole and then we have an ion. The ion here is charged. A dipole is partially charged. So we expect them to interact to form a solution. But let's take an example. Pentane. Pentane and water. If you mix pentane and water, pentane uses dispersion forces. These forces do not have any dipole, while water uses hydrogen bonding. So the question is, can pentane dissolve in water? The answer is no. They have two different forces that are responsible for dissolving. Dispersion forces are not in line with the hydrogen bond. Hydrogen bond can work, these three forces can work together. These three can work together, but not this one. This one is different because all these have polarity of some sort. These ones are not polar. So a polar will dissolve in polar. Non-polar will dissolve in non-polar. But these two, polar will not dissolve in non-polar. That's where this term comes. Likes dissolve likes. And that's why we are saying forces that may contribute or oppose. So if you mix dispersion and hydrogen bonding, there will be an opposition to making a solution. If you mix dispersion and dispersion, there will be a contribution. If you mix hydrogen bonding, you are contributing to a solution. If you mix a dipole and a hydrogen bond, you are contributing to a solution. And really, also still when talking about solutions, for a solution to form, there must be some interactions that are happening in a solution. So as we said, there are these three types of interactions: solute, solvent, that is 1, 2, solvent, solvent, 3, solute, solute. Now, when does a solution form? That is when the two particles, solvent and solute, when the interaction between solvent and solute is greater than the interaction between solvent and solvent, or solute and solute. So what we are saying is, if we have a solute here and another solute here, and then we have a solvent here and another solvent here, we want these to interact more. We want these to interact more than these two, because if you are forming a solution, you want this interaction to be stronger. You want this to be stronger, and you want this or this to be weaker. So solute, solute, weaker. Solvent, solvent, weaker. Solute and solvent. Solute and solvent, stronger. That's what you want to do. That's what it means here. In that case, the solution forms. The second scenario is if solvent and solute interaction is equal to solvent, solvent, and solute, solute interactions, the solution is also going to form. Now the third situation is tricky. If solvent solute interactions are less than solvent solvent and solute solute, a solution may form or may not form, depending on how strong these are. If they are too strong, the solution is not going to form. If they are greater than this but not too strong, the solution may form. So really, it just depends on the situation. But what you want for a solution is for solvent and solute interaction to be strong, instead of solvent solvent and solute solute. So let's take note of these relative interactions in the solution formation. So these are the interactions that we are talking about. This is one species interacting, that is solvent solvent. This is solute solute interaction, but what we want is a stronger this. This one should be strongest for a solution to form. So let me just get rid of this part. So we want this to be strongest in this case. Now, talking about solutions, because they involve moving things around, definitely energy is involved. So we have three energetics that are important in forming a solution. First of all, let's say you have your solute, and this is our solute. For a solution to form, you want to break the particles of the solute apart. So you need to get rid of these interactions here. What do? You need to put energy into the system to break the solute to particles. In that case, your energy is positive. because this process absorbs energy. You need an energy input to break the interactions among particles. That is, we call it enthalpy of solute. Enthalpy of a solute is always positive. What about the solvent? You need to do the same thing with the solvent. You need to create space for the solute to be in. How do you do that? You add energy. So you add energy here. Once the energy is added, it brings the solvent particles a little further apart so that we create space for the solute to get in. So as you can see here, this process involves addition of energy. So we can say enthalpy of a solvent is always positive. Then we have a third enthalpy. Now after you bring this further apart and also you bring these further apart, now we need these particles to get into these spaces like we see here so that we have a solution. Now this process is negative. So we say this process is negative. Why is it negative? Because you are bringing things together. So the enthalpy for this process is negative. As you can see here, the enthalpy of mixing is less than 0. So for a solution to form, you need all these three enthalpies to come together. If you are using a diagram like this one, what does it mean? Here, it means you have your solvent here, and then you have your solute. Both of these need energy. You add the enthalpy of solute, you separate the solute. Then you add the enthalpy of solvent, you separate the solvent. When the two separates, you mix them. In terms of mixing, you lose energy. That's why the arrow is pointing down. While in terms of separating them, you gain energy. That's why the arrow is pointing up. But the solution process itself, here you have lost more energy than gained. So you lost more energy than gained, because in terms of gaining, you gain energy from here to here, from here to here. In terms of losing, you have lost way more than that. So the actual energy of solution where's this pencil doing? The actual energy of solution will be less than 0, because the net, the arrow is pointing downward, and this process is known as an exothermic process. So an exothermic process occurs exothermic occurs when energy of mixing is greater than energy of solutes plus energy of solvent. So this means you have lost more energy than the energy you have gained. But there is another process where you actually add more energy into the system than the energy you lose. So in this case, you add more energy. That is, the enthalpy of solute plus the enthalpy of solvent is greater than the enthalpy of mixing. So delta H solute plus delta H solvent is greater than delta H mixing. In that case, when you add all these, because this one is supposed to be negative, these two are positive. When you add all these, they are going to give you a positive number, and the reaction is going to be endothermic. So what does it mean? It means a solution can form under exothermic process or endothermic process. Have you ever dissolved something? Like if you dissolve sodium hydroxide. If you dissolve sodium hydroxide, and hold the cup containing the sodium hydroxide, the cup, your hand will feel hot, indicating that you have an exothermic process happening in that. The reaction is releasing energy to you. If you dissolve something else, your hand will feel cold, indicating that the reaction happening inside the container is endothermic. But in both cases, dissolution is occurring. So really, dissolution can occur under exothermic process and endothermic process. What matters is the mixing more random? That's the final determinant on whether or not a dissolution is going to occur or a solution is going to form. What matters most is the randomness of the solution after mixing. If you increase randomness, a solution is going to form. If randomness does not increase, then a solution is not going to form. That's how it works. So you can have an endothermic reaction where randomness of the solution increases. We have our solution. You can have an exothermic process where randomness of the solution also increases. We have our solution there. We cannot talk about solution without also talking about hydration. So, for example, you take sodium chloride. When you dissolve sodium chloride in water, the sodium ions and chloride ions separate. So this sodium has a center of positive, the chloride ion has a center of negative. So if you have water hydrogen is partially positive and oxygen is partially negative. So the positive part of the water is going to surround the chloride ion. The negative part of the water is going to surround the sodium ion. That process is going to separate chlorine and sodium apart, and we call it hydration. So really, hydration is just the surrounding of the solute, the surrounding of the components of the solute by the solvent. So surrounding of the components of a solute by a solvent. Sometimes it may not even be components. So like in this case, we have sodium plus and chlorine minus. These are components. Sometimes hydration can occur even without surrounding components, but surrounding the actual molecule. Like in sugar. In sugar we have glucose. So C6H12O6. This glucose molecule is surrounded by water molecule, also to make kind of a hydration. But normally the usual hydration is when we have components of a solute surrounded by solvent molecules based on the charges. So I'll add here based on the charges. So what do we mean by when we say now the heat of solution, enthalpy of solution finally? So the enthalpy of solution occurs when you add the enthalpy of solute, enthalpy of solvent, plus enthalpy of mixing. These two, when we add them, enthalpy of solvent plus enthalpy of mixing, are known as enthalpy of hydration. So solvent and mixing will make hydration, because for hydration to occur, we should have those solute molecules already separated, and then we'll need to separate the solvent molecules so that they go and surround the solute. That's why hydration involves the solvent and the mixing energy. So usually hydration will be exothermic, because the mixing is always bigger than the energy of mixing is always bigger than usually bigger than the energy of the solvent. So hydration will be most of the time negative, but really it will depend. For this to be exothermic, it means hydration energy should be bigger than this, because this one is always positive. So hydration energy should be bigger than this, and then we'll have a negative here. If hydration energy is smaller than this, then we'll have a positive here, and we can refer to that solution as exothermic or endothermic. So I'll just show you these examples of exothermic solution. If you dissolve lithium bromide in water, you are going to have negative energy. That is, the process releases energy. If you dissolve ammonium nitrate, so this is ammonium nitrate, if you dissolve ammonium nitrate in water and you hold the cup will feel, container will feel cold. So here the container feels cold, while here container feels warm. So there are other situations where you have solute is equal to hydration. In that case, the enthalpy of solution will be close to zero. So one example is if you dissolve sodium fluoride or sodium chloride, the enthalpies will be close to zero, because in that case hydration is, energy of hydration is equal to the energy of solute. So this is the introductory part of chapter 13, that is solution. Make sure that you watch the video and you deal with the video assignment. Thank you.